So we want a acid with a pKa of around 7, which P is power function, so a power of around 7. It's actually the negative power, but if we look down the list here, and here's one. This is perfect, because this has a pKa of 1.0 times 10 to the negative 7. This would be called dihydrogen, what's that anion? Arsenate. Dihydrogen arsenate is perfect. Except for one thing. Arsenic, what do you know about arsenic? It's highly poisonous. And so we don't want something that's going to be highly poisonous. So we aren't going to use this here, even though the pKa is exact match. Because if we have a pKa of this, what is our base to acid ratio going to be? Our base to acid ratio is going to be 1 to 1, that means it has equal versatility in neutralizing added acids and added bases. But let's continue down the list here. No, I'm not close. Okay, this is kind of close. 8.9 times 10 to the minus 8. Hyponitrous. But hyponitrous, that's kind of not a very common one. Probably expensive, so just forget that one. Let's cut down the list. 2.0 times 10 to the minus 6. It's kind of close. This would be what we call hydrogen. Malonic acid would form malonate, the anion. So hydrogen malonate. And so this is a candidate potential, but let's see if there's something closer. So we're looking for something in the range 6, 7, 8. And so 10, 5, 3, 5, 7. Here we go. Carbonic. We could do carbonic acid, but the problem is what carbonic acid is? Carbonic acid stable? Can you just go to the? No, you can't go to the store and buy it. It has to be made, and it doesn't last very long. And carbonated beverages have carbonic acid, and when you open the cap, that carbonic acid goes. CO2 and water. And the carbonic acid is impractical. 11, 3, 2, 4, 5, 7. Here we go. We could use this one. This is called monohydrogen citrate. Citric acid is a triprotic acid, so it's Ka1, Ka2, Ka3. If we use monohydrogen citrate as our acid, that would work. It's very close. Cyan, except there's one problem with citric acid or monohydrogen citrate. The one problem? The one problem with citric acid is it's fairly electron rich, and that means it's easy to oxidize. And so citric acid and monohydrogen citrate doesn't last forever because it's exposed to air, it gets oxidized and decomposes. And so probably would rather not use this because of the shelf life issue. Going down, no, nothing here. Let's check this side. Here, this one is close. If this were 10 times 10 to the minus 8, that would be 1 times 10 to the minus 7. And so this is pretty close. This would be dihydrogen phosphate. Use dihydrogen phosphate. This we could use too. This is pretty close too. This is dihydrogen phosphite. But is phosphite and phosphorus acid very common? Have you seen that much? No. It's going to be more expensive. Okay, this one is okay, dihydrogen pyrophosphorate. But this is a quatroprotic acid, K1, 2, 3, 4. But this is not very common, and it's going to be pricey, so we aren't going to use that. All right, this is very good here. This is right on, 1.0 times 10 to the minus 7. That's a perfect pKa, because the pKa of this would be 7.00, right? Except there's a problem with H2S. Do you know about H2S? Rotten eggs? One, it smells so bad. Two, it's highly toxic. This stuff will kill you at the part per billion level in air, so we're not going to use H2S. Three, there's another problem, which you probably don't know. It's not very soluble either. So here, hypochlorous acid would work. HOCl. This is bleach. Bleach doesn't smell so good. Let's avoid that. Thiophenol. Thiophenol, you spill one drop of thiophenol on your shoes, you'll have to throw them away. But before you throw them away, you'll wrap them in plastic bags because it smells so bad. Thiophenol. This is skunks. Skunks have a lot of thiols in there. Oh, yeah. I know this for a fact because my friend, lab mate of mine, spilled a drop of this on his shoes. He wrapped it up in 3 garbage bags and threw it away in the garbage. True story. So which one do you want to use out of all those? Well, yeah, dihydrogen phosphate. This seems like the best one. So even though the pKa is not perfect, it's close, you know. And so we're going to use dihydrogen phosphate. And then let's try to make a buffer out of that. And so first thing we'll do is we're going to figure out what is the pKa for dihydrogen phosphate. And so dihydrogen phosphate is a good candidate because it's cheap and it's readily available. And it has a Ka of 6.2 times 10 to the minus 8, which is fairly close. And, 6.3. This book's chart and room chart confuse me. 6.3 times 10 to the minus 8, sorry. Which gives it a pKa of what? We'll just take the negative log of that. .2. I'll give you more digits. We're allowed 2 sig figs. 0. One more. 0. 7.200. Is that what everybody got? Okay, good. So it's 0.2 units too high. If it's 0.2 units too high, we need to bring the pH down by 0.2 units. Do you know how we bring the pH down by 0.2 units? We add more acid. And so if we just add a little bit extra acid compared to the base, the pH should drop a little bit. And so what we got to do is we got to figure out how much extra acid we need to add. And so to do that, the next thing is we want a weak acid, so we got that. Then we need to determine the ratio. You know, this is plus or minus 1, so we're still in the buffer region. You know, we need anything between 6 and 8, so this is good. Then determine the ratio. You know, the base to acid ratio. So, okay, let's do that. Remember that these have to be conjugates. So when I write this, I don't want to confuse anybody. Conjugates. And so the pH is equal to the pKa plus the log. Now, the base, I don't know, but I know the acid. The acid's got to be H2PO4 minus. What is the base in that case? So we figured out what the acid is. Now we got to figure out its conjugate base. What is the conjugate base of H2PO4 minus? H3PO4 would be the conjugate acid. And so this is the acid. This has to be the acid. Therefore, the base has got to be HPO4 2 minus. Okay, that's because this is H2PO4 minus as our acid. All right, so what that is going to give us is this equation here. Now to solve for the ratio, this is what we do. We put in our desired pH. Let's do that. Our desired pH is 7.00. This is going to equal to pKa 7.20 plus the log of the base to acid ratio, which would be HPO4 2 minus over the H2PO4 minus ratio. And so we're going to get the log of this ratio is equal to negative 0.20. Then we take the anti-log of both sides. If we take the anti-log, we're going to get the HPO4 2 minus over the H2PO4 minus ratio is going to equal 10 to the minus 0.20, which is going to give us what? .630. 0.6309. All right, so what this means is that I would have 0.6309 parts of base for every 1.0, let's go with 00 parts of acid. Is that okay? Yeah. Actually, this is just two things. One is exact.
Where did the one come from?
Well, actually, it should just be one. For every one part of acid, for every one part of acid, we have 0.63 parts of base. Or we could invert this. If I invert this, then for every for every one part of base, we would have 1.584 parts of acid. I'm only allowed 2 sig figs.
How do you know it's put one underneath?
How do I know it's 1? Oh, it's like this. You know, if I get 10, I can just say 10 to 1. You know, instead. That's equal to 10. So any number we can divide by 1. Since this is a ratio, I'm just going to divide it by 1. So let's figure it out. Or anything that makes this. And so what I could do is I could do this. I could make the acid 1 molar and the base 0.63 molar, and that would give me a pH of 7. Or I can make the base 1 molar and the acid 1.58 molar, or anything in between. And so an example of this would be, I'm going to make the acid H2PO4 minus 0.250 molar. What is the base concentration going to be? Well, I just have to have that ratio. And so in order to figure out the base concentration, I would just start off with 0.250 molar H2PO4 minus, and then I know the ratio. Here. For every 1 molar H2PO4 minus, I need 0.6309 molar HPO4 2 minus. And so that would be 0.25 times 0.6309, which gives me 0.157 molar. And so if I mix up a solution of 0.250 molar H2PO4 minus and 0.1577 molar HPO4 2 minus, that should give me a pH of 7. It would be a buffer. This buffer would have slightly higher acid capacity than base capacity. You see that? Because we have more acid, therefore it can neutralize more added base. But it isn't totally lopsided. It's still within the 10-to-1 ratio. That makes a decent buffer. Obviously, I could make it, if I want to save money, I could just make it very dilute, right? And so another example of this would be, I could just make it quadruple 6, what is it, 6, what was the original ratio? 637?
What's 639?
6309? Okay, so if I made it like this, the base to acid ratio, what would the pH be? The pH would be the same. The pH would be 7.00, right? Because all it depends on is the ratio. It doesn't depend on the actual concentrations. As long as the ratio works, then the pH should be 7. But the problem with this buffer is it has very low. What is the problem with this? Even though the pH is right, the problem is it has very low capacity. This buffer would not last very long because what we'd say is it can be easily overwhelmed. So for example, if we just add a little bit too much HCl, it'll completely react with all the base and it's gone, and then we no longer have a buffer. Okay. And so that is a problem, easily overwhelmed. And so what we want is we want the buffer to be the excess reagent, be in large excess relative to use. And so we want plenty of capacity. So what we'll do is we'll just make this. We'll have pure water. Pure water should have a pH of 7.00, 25 degrees C. And then we're going to make a buffer. The buffer here is going to consist of, we'll make it 0.6309 molar HPO4 2 minus and 1.00 molar H2PO4 minus. And this should have a pH of 7.00. If we plug this back into the Henderson-Hasselbalch, that's what we should get. So then A, we're going to add. Let's do this. We're going to go with about a cup. A cup is how many milliliters? 250 milliliters, you say? So let's go with 250 milliliters of water and then 250 milliliters of this buffer. And then A, we're going to add a drop of dilute HCl, 6 molar HCl. Let's go with 6.00 molar HCl. And then we'll do another calculation after this. So if we add a drop of 6 molar HCl, we're going to add it to both. So over here we'll have some HCl, and here we'll have some HCl. Now in chapter 17, there's going to be a step I. From here on, after the buffers, buffers, we don't care about solution dilution. But for all the other problems in chapter 17, we care about solution dilution. And so from here on out, we're going to do step I, which is equal to solution dilution, initial step. Do you know about how much volume a drop is? A drop is roughly 0.05 milliliters. And so we'll just use 0.05 milliliters to represent the drop of water, of HCl, excuse me. And so let's do pure water first. If we do pure water, we're starting off with 250 milliliters of just H2O liquid. And then we're going to add a drop, plus 1 drop of 6.00 molar HCl. And that means we're going to end up with 250.05 milliliters total, because the volume is going to go up by a drop. Normally we'd say, oh, that's small, it's negligible, so we ignore it. But from now on, we aren't going to ignore it. We're going to, going to add that in and see what happens. And so the solution dilution is going to be like this. Now the concentration of HCl in here is equal to what? Well, we use this equation M1 V1 is equal to M2 V2. We solve for M2. M2 is equal to V1 over V2 times M1. V1 over V2 is called the dilution factor. And so what is the dilution factor here? Well, the dilution factor is the HCl, we're going from a volume of 0.05 to a new volume of 250.05 times the original concentration, which was 6.00 molar. So this is going to be diluted by a huge factor. Looks like if we move that 2 decimal places over, it looks like a 25,000 time dilution, or 20, something like that. Well, anyway, or I should say 10,000. Something. Well, anyway, we can do the calculation and figure out what the concentration is. And so the new concentration is, we just added a whole bunch of water to the HCl. That HCl is going to be very dilute now. And so what is that HCl going to be? HCl is going to be 0.05 divided by 250.05 times 6. And it gives me a concentration of 0.001199 molar HCl.
Sorry, Professor, what's the number underneath 0.05?
250.05. That figure. Where did that come from? This is V1. Actually, this is V1 here. This is V2. V1 is 1 drop. And so V1 is 0.05, V2 is the new volume afterwards. All right, now we have acid and water, so what do? We do the Ka and all that other stuff, right? And so if we have this much, we're going to get this much hydronium. And so this is going to yield 0.001199 molar hydronium, because Ka is large for HCl. Ka is very large. So I'm skipping the ice table for this. Now we got to think, well, that's not the only contributor. Ka, and then this is monoprotic, and then Kw. Should I worry about Kw here? Yes or no? No, I shouldn't worry about Kw. Why?
Because we only use the first step for pH.
Well, sometimes I have to worry about the second step. And so why in this case don't I have to worry about the second step?
A is very large.
Well, yeah, but we saw a Ka that's very large before, H2SO4. H2SO4 has a very large Ka, but we still did the second step. You'd have to do the second step, otherwise you get a wrong answer. Well, yeah, but if you go back to H2SO4, we did step 2, which is a weak acid, HSO4 minus. The reason I'm going to ignore Kw here is because what is the most hydronium Kw can contribute to this? Did the thing is, I'm doing this, a whole variety of problems. We did HCl before. We did HCl before where we had to worry about Kw. If you didn't do Kw, you missed 90% of the hydronium. Do you recall that? That was the 1 times 10 to the minus 8 molar HCl. If you did 1 times 10 to the minus 8 molar HCl and you said, I'm going to stop at step 1 because Ka is very large, then you just made a huge error because you're going to get pH of 8. pH of 8 is not acidic at all, it's basic. And so the difference between this HCl and the HCl we did a long time ago is the concentration. The concentration is much higher here. And so this is 0.001. So there's a 0.001. What's the most hydronium we're going to get from Kw? The most is 10 to the negative 7, but we're going to get a lot less because of the common ion effect. We're going to get like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10. And therefore, will 10 to the minus 7 even impact this? No. And so the reason we're going to ignore Kw is because an addition of 10 to the minus 8, 10 to the minus 9 molar hydronium will have 0 impact on this. Therefore, we ignore it. And so we assume Kw is going to be negligible here. We'll stop here and determine the pH. What is the pH? What happened to the pH of water? The pH of water went from 7, this is pH 7, to, we'll just take the negative log of this. 0.0, oops, I should have just left it in the calculator, 1199 log 2.92. The pH is going to go to 2.921. So power functions are powers of 10. And so if we go from 7.00, this is about 4 orders of magnitude. And so the water just became 10,000 times more acidic. We want about 4 powers, about 10,000 times. And so just by adding 1 drop of HCl to a cup of water, I wouldn't want to drink it. That's pH 3. Whereas, the 10 to the minus 8 molar, I'd drink that. I remember in high school chemistry, the high school chemistry teacher always told the class, if you mix HCl and sodium hydroxide, you're going to get salt water. He said, I would drink it, but he never did drink it. I was waiting for that. So I thought, well, maybe he doesn't have enough faith in chemistry, But anyway, let's go on to this. What happens if we do the same thing with the buffer? What would the pH change? This pH changed dramatically here. With the buffer, we're going to have, stop soon. Okay, we're going to have whatever it was, and then we're going to add 1 drop of 6.00 molar HCl. Now, in the chapter 17 problems, what we're doing is we're mixing 2 solutions together. Whenever we mix 2 solutions together, like an acid solution, base solution, we have to do a solution dilution. We avoided doing that in chapter 16. The way we avoided doing that is we started after we did the solution dilution. And so we gave you all the molarities, the initial molarities after solution dilution. In chapter 17, we're not going to do that. In chapter 17, you're going to have to do the solution dilution. So if we add even a drop, then we're going to get a new volume. And so the new volume here is going to be 250.05 milliliters. And that means we have to recalculate all the concentrations. And so the HCl concentration, we already did that calculation there. It's the same dilution factor, 0.05 to 250.05. So we'll end up with the same diluted concentration. So this is going to be 0.001199 molar. And then we're also going to dilute the monohydrogen phosphate. Okay, the monohydrogen phosphate, which is the base component, was 0.63 whatever. But what is the dilution factor for this? The dilution factor is going to be a 250 to 250.05. Well, in this case, that's pretty much a negligible dilution, right? And so the concentration will not change much. But we'll still calculate it because we got to do this now. In Chapter 17, we always have to do this for all the problems from here on out. And so this is going to be 0.6309 molar. And so what does that come out to? It's going to come out very close. Probably a very negligible change. And so I would do a 250 times 0.6309 divided by 250.05. And so the dilution factor is almost 1. And so that means the concentration is just going to be about the same, 0.6307. So we went from 0.6309 to 0.6307 molar. Not much change. And then we got to do the same thing for H2PO4 minus. The same dilution factor, is it started off in the same beaker, 250 to 250.05. Dilution of 1.00 molar. And so what's 250 divided by 250.05? And this is going to come out to 9998 molar. All right, so in Chapter 16, this is where we start the problem. You know, these are all the concentrations in the same beaker. Now what do we do? Okay, so this is an additional step that we have to do in Chapter 17. Okay, but now what do we do? Now we got this mixture. What do we do with that mixture? Well, we do the same thing we do for all problems in Chapter 17, unless we recognize, quickly. If we recognize, hey, that's a Henderson-Hasselbalch buffer, we can save a lot of time. But what do we do for all problems in Chapter 17? We do the same approach. The same approach is to take the strongest acid and react it with the strongest base. Now this mixture is more complicated. We got more species in there, and some amphoterics, whatever. But in this case, the strongest acid is going to be, can you see it right off? The strongest acid is going to be hydrochloric acid. And then we figure out what is the strongest base. The strongest base is going to be HPO4 2 minus. And so what is this going to yield? Yeah, this is going to yield H2PO4 minus plus chloride. Now we have to figure out what is K for this. What is K for this reaction? And so I'm going to give you this K. The K for this is strong react to completion. And so that's an acid. That's an acid we know. HCl plus water. HCl plus water goes to hydronium plus chloride. What is Ka for this? Very large. Now we have to ask ourselves, is HPO4 2 minus a better base than water or worse base than water? This is a better base. If this is a better base, then we're going to say that the K for this reaction is very, very large because it's a better base, right? What if we did this? We reacted with sodium hydroxide. If we reacted with sodium hydroxide, then that is an even better base, which means that K for this reaction is going to be very, very, very large. And so I already know the K value for this because this is HCl that's a better base than water, then K's got to be very, very large. This is a weak base. And so K is going to be very, very large. That means this is going to react to completion. So the HCl is going to be 0.001199 molar. The HPO4 2 minus was going to be 0.6 what is it, 307. The H2PO4 minus is 0.9998 molar. Is that right?
Yes.
Yeah. And the chloride, we're assuming no reactions taking place yet. And so we put in all the initial concentrations of this mixture in here. And then we react this, well, K is going to be very large. So what is the limiting reagent in this reaction? The limiting reagent is going to be the acid. And so the limiting reagent gets completely consumed, which means this is going to be minus 0.001199 molar, which is going to give me 0.62. What is it? Actually, I'm going to just calculate it. I'm going to do it in my head. And so this 0.6307 minus 0.001199 gives me 629501. 629501 molar. And then this is going to be plus 0.001199 molar. Getting lazy. So let me just do 0.9998 plus 0.001199. Excuse me, 1.000999 molar. And then the chloride is going to be 0.001199 molar. But it looks as if we have the same problem, because if I want the pH, I don't have any hydronium present or hydroxide present. I can calculate the pH of the POH, right? And so what do I do next? What I do next is I analyze this mixture and see, what do I have left in this mixture? And so what I mean by repeat is we would repeat the process. We would take the strongest acid remaining and react it with the strongest base. What is the strongest acid remaining? H2PO4 minus. What is the strongest base remaining? HPO. Hey, didn't we do that earlier? Didn't we waste a whole lot of time doing that? We certainly did. We did that reaction, right? Wasted a heck of a lot of time. If we just recognize that that mixture is a, this is a weak acid, weak base. This is a Henderson-Hasselbalch buffer. That's a Henderson-Hasselbalch buffer, then the pH is easy. The pH is equal to the pKa plus the log of the base. Okay, so this is the pKa of H2PO4 minus. The base is going to be HPO4 2 minus. The acid is H2PO4 minus. And so let's figure out that. And so I'll take the base and divided by the acid. We'll take the log of that, plus 7.2. And it comes out to 6.998 as the pH. All right, which rounds to pH 7. So if I add a drop of HCl to my buffer, note one thing. I have lots of capacity here. And so the buffer remains. The ratio changed slightly, but the buffer remains here. And so I started off with the buffer. I end up with the buffer, but the ratio changed slightly, but not enough to really change the pH. The pH dropped a tiny bit, but not much.
What did you add for the pKa to the
7.200. pKa is 7.200. And then I just plugged in these concentrations here. And then I'm done, because what happens is if I add a drop of HCl to the unbuffered water, the pH changed a factor 10,000. If I add a drop to this buffer, then no problem. The situation is I have to have good capacity, because let's say I wanted to skimp on the capacity. I wanted a cheaper buffer. Are we okay with this? Do you guys see that the pH?
Where did the 7.2 come from?
7.2 is the pKa of H2PO4 minus. Because this would be the acid, this would be the base, is defined by the combination. And so we take the pKa of the acid H2PO4 minus, which is, we calculated earlier at 7.200 in the ratio. Okay. I'm trying to speed up here, so this is why I'm not writing.
So that's just the concentration of the 1.00 over the 0.6295.
Yeah, so I plug this in here. I plug that in here, and I plug this in here. Because we already tried doing additional steps beyond this, but it didn't really work out so great. And so we just end up with this, but unfortunately it's just a Henderson-Hasselbalch buffer. And therefore, we just use the Henderson-Hasselbalch equation.
Don't you use initial concentration when you do the log?
No, this is the initial concentration. What we had was, before, this is not a Henderson-Hasselbalch buffer.
Oh, you reset it, right?
No, I reacted it. This is not, the top is not a Henderson-Hasselbalch buffer because you got HCl. This is now the strongest acid present. Both of these are going to be bases. It's not a Henderson-Hasselbalch mixture. And so after step one, then what we're left over with after reaction is a Henderson-Hasselbalch buffer. And so this is the initial starting point for the next step, which I'm skipping because I know that Henderson-Hasselbalch will work. So I can skip the ice table. So anyway, getting back to this, I add a drop of 6 molar HCl. The base component of that neutralized it. Do you see how the base neutralized that? Here. So there's no more HCl, but in the process of neutralizing it, we sacrificed a little bit of the base component and made some more acid component because that's the product. And so the buffer did its job, basically. The problem is if I overwhelmed it. If I only add this much HCl, no problem. But what happens if I add, let's say, 0.5 molar? If I add 0.5 molar, then I'm going to see a more dramatic change. But I'm still going to have buffer left over because all the acid will be consumed. And so the acid will go down to 0, but now there's going to be a more dramatic change in the ratio. A more dramatic change in the ratio means that the pH is going to see a more dramatic change. But still it's going to be buffered. What if I overwhelm the buffer? This is called overwhelming the buffer. If I add 1.0 molar HCl to this, then what's the limiting reagent? We want the buffer to be in excess, but now the buffer is the limiting reagent and it's no longer going to be buffer. It's going to be what we're going to call a strong acid, weak acid mixture.
So for the log ratio, the HPO42 minus, that's the base.
Yeah, this is the base, this is the acid here. It's the base to acid ratio. Just memorize that. And so we don't want to overwhelm the buffer capacity. Does that make sense here?
If you have a majority of...
All right. What we want is this is our buffer here. We want our buffer to be in excess always. And that wasn't the problem here because this was what, 0001199. And so we're just adding a little bit. But if we add too much acid, that's going to overwhelm our buffer. And so if the acid is, let's say the acid were 6.00 molar, then there's no way this buffer can handle that. That's one thing. But then we might increase the capacity. Well, if we increase the capacity of this, we can make this 63 molar and this one 99 molar. If we make it 63 molar, but is it possible to make 63 molar? No. I mean, you can't get that concentration because that's like can you dissolve 10 pounds of salt in a cup of water? No, it's not going to work. And so to make this, it's not going to happen. Even pure water is 55 molar. And so the capacity is this. What we want is whatever we add to it, added acids or added bases, we want the buffer to remain at the end. The ratio is going to change, and then we just recalculate the pH. Okay, the next calculation we'll do later, but the next calculation will involve overwhelming the capacity of the buffer, and then we'll see a more dramatic change in the pH.
Why do we want the buffer to remain at the end?
Why do we want the buffer to remain at the end is to minimize the impact on pH. The main purpose that people use buffers is to have a stable pH. Like our blood. Do you know our blood is buffered at pH 7.4? Do you know if the pH of your blood changes by 0.4 units, you're in trouble. So if your blood went from 7.4 to 7.0, you're in serious trouble. Or if it went from 7.4 to 7.8, you're in serious trouble. But, you know,
So the buffer is just like
the buffer is to maintain a stable pH. What happens is, you could see this. Have you ever added acid to eggs? You know, when you add acid, you change the pH, all the proteins in the eggs denature and come unfolded and do whatever else. It's like cooking an egg if you pour acid into an egg. And that's just, you know, pH change is going to screw up all the structures up. And so pH, maintaining a stable pH is especially important in a lot of biological systems because the structures depend on these intermolecular forces which can get disrupted with those, and also charges and other stuff. Okay. But we also use buffers for many other purposes as well. Like, for example, precipitating out the 3+ cations and leaving the 2+ cations in there. There is actually a pH. There's a pH that we have to maintain in order to do that. And that's why we had to buffer the ammonia a little bit. Okay. It's a pretty wide range, so it was pretty loose and flexible. But if we didn't buffer it, we would have gotten the 2+ cations precipitating. Okay. All right. Well, I'll stop here and then